This episode is sponsored by CuriosityStream. Right now, it requires multi-million-dollar rockets launched from enormous facilities to take a person into space. But what if you could fly there from your driveway? I was quite the sci-fi junkie when I was a kid, and I still am. But like many folks who grew up watching the old space operas, I always envisioned future spacecraft as something you might have in a shoddy hangar owned by a couple of regular guys, or a smuggler and a Wookiee. That wasn't much different than an enthusiast boat or yacht. Growing up then, with the space shuttle launches and the SR-71 Blackbird in the skies, there was always regular discussion of a concept called a spaceplane, and I thought we'd take a look at that option today, and if it could ever be a pathway for cheap and easy travel, not just from ground to space, but from your own garage right to another planet. Now, nothing like that is on the drawing board yet for actual deployment, and we'll discuss what's needed for such an option and what it might mean for our civilization if we had them. But we do have quite a few experimental spaceplane models that have been developed over the years, and they are quite viable. Some of the original designs actually work better now with new materials and more advanced engineering. While there's always more testing, prototyping, and improving to be done, we haven't used them mostly because we had options seen as equal, better, or simply cheaper that we'd already invested in. But let's start with the basics. As we've discussed before, rocket propellant is measured in specific impulse, basically how many seconds the engine could keep a craft hovering before it ran out of fuel. For that reason, they need to get themselves into space quicker than that, since they have to generate far more thrust to achieve escape velocity than just hover in place. Your typical rocket propellants have mere minutes of specific impulse. 6 to 8 minutes worth is very good for a modern rocket. But jets do far better, and your typical turbofan might have multiple hours of specific impulse. The reason is simple enough. Rocket fuel is about burning a fuel with an oxidizer and firing a propellant out the back. The oxidizer, usually oxygen, is something you only have to carry with you once you get up into space, where there isn't a need to pull out of the air. Folks would wonder why we don't just get the planes up to orbital speed, and maybe a bit higher, in the atmosphere, so they can just coast into orbit. There are some problems doing that, but at the very least, why don't we strap the rocket on the back of a very fast plane, then launch it once that plane has peaked out? We talked about that a little more last time in the series with sky platforms, but I mentioned there I'd explain how this whole air-breathing jet thing worked and why it's a problem. A bit over a century ago, the Wright brothers got us our first aircraft, which at its most basic used an engine to turn a propeller. This made the plane go, but not really all that fast, and we introduced the jet engine about half a century later. A jet engine is actually a fairly simple concept too. You use a fan up front to suck air. That's not too tricky in some respects, since once you're moving, a bunch of air is slamming into you anyway. Some of that is poured inside while some goes around to help with cooling, and will rejoin the flow in the last step. The core of the engine consists of the compressor, combustor, and turbine assemblies. The turbine and compressor are joined by a shaft. The compressor draws air into the core, compressing it up to 50-fold. This air has a lot more potential energy as it enters the next stage, the combustor. The combustor is where fuel is injected. The heat generated by compressing heats the air to around 400 degrees Celsius, sufficient to ignite the fuel. This burning high-energy air slams into a turbine and makes it spin, which powers the fan and compressor on turbofans, which are in most modern engines. It then exits through the nozzle, where it mixes in the last step with the cold air I spoke about earlier that went around the engine, and blows out the back, producing thrust. This jet engine turbine concept is applied to the turbojet, the turbofan, and the turboprop. which are just a mix of the word turbine with jet, fan, or propeller. It's easy for folks to forget that the word turbo, used so often in modern English to mean something powerful and fast, originates from this object, the turbine jet or turbojet, though turbine itself comes from the Latin word turbo, which is a spinning top. Counterintuitively though, the turbofan is common in modern planes, not so much because it makes the planes faster, but because it makes them more efficient at lower speeds. This is why it tops out on lists of engines and rockets in terms of specific impulse. It's actually not that fast, but it's way more efficient at subsonic speeds, which is why it's the main type used these days. We also have the afterburner, very literally named, where you spray more fuel in to burn after the main phase through the turbine. This is very inefficient, but nice for a quick boost of speed, and saves you the weight of another or larger engine. Notice I said that jet engines aren't all that fast. In fact, none of these are going to get you up to anything like orbital speeds, and even afterburners usually won't let you get much above Mach 3. That sounds fast, but we need about Mach 23 to get into orbit. Of course, part of the problem with getting faster is all that air slamming into you is also trying to slow you down. And as you get higher, where it's thinner, it's hard to get enough air for that turbine. So we get the ramjet, also known as the flying stovepipe, and these start working well once you get to about Mach 3. They don't work at low speeds at all, because we need air traveling at about 400 miles an hour ramming into the intake for it to work. Anything with a ramjet will always have normal jets to get up to speed first. Moving parts in a jet at that speed are a problem, and not necessary, so ramjets have no moving parts. There's no propeller, turbine, or fan in there. They rely on the sheer force of air ramming into a static cone while we burn fuel inside, superheating it, and expanding burning air pushes itself out the back even more forcefully than the air coming into the ramjet from the front. This works very well as a second engine for higher speeds. The hotter the burning gases, the more push they have and the faster you can go. The downside though is that these hot burning gases tend to melt things, like your ramjet. So ramjets can boost our spaceplanes to hypersonic speed, up to Mach 6. That's fast, enough to circle the Earth in around 5 or 6 hours, assuming you didn't run out of fuel first, which you would. But we are still well short of that very fast Mach 23 orbital speed. We next get to the scramjet. While the ramjet sucks in supersonic air and decelerates it to subsonic speeds to compress it, the scramjet, or supersonic compression ramjet, works at even higher speeds, and while it slows the air on entry to compress it, it never slows it below the speed of sound. The speed of sound changes as we change altitude, and it isn't linear either. At ground level, it's 343 meters per second when dry and at a normal temperature. It drops as you go up, down to around 300 meters per second between 10 and 30 kilometers of altitude. Then it reverses again, sharply rising as you approach the stratopause 50 kilometers up, where it's almost as fast as on the ground, then dropping again as you approach the mesopause at about 85 and 100 kilometers up. Then it rises again as you basically leave the atmosphere, shooting up to hundreds of kilometers per second, though sound starts being a fairly meaningless concept as you approach vacuum. That constant change in air pressure, temperature, speed of sound, and so on is a big issue with aerospace vehicles in general, and one of the reasons we use multiple stages with different engine types so much. One of the ways around that is what's called an aerospike, where the exhaust forms a narrow spike instead of the classic big bell-shaped rocket nozzle. Ideally, you want your thrust coming out with every particle moving exactly backwards, and the bell shape basically sprays them out on mini trajectories, losing a lot of thrust. The aerospike focuses them in as straight a line as possible. It's the core concept behind the X-33 design and its big brother, VentureStar. Aerospikes are more fuel efficient, but do come at a cost. They need more cooling and are quite heavy. which is never a good thing for objects trying to fly or get into orbit. Variations on them include the linear aerospike, which looks more like a big wedge, and a toroidal shape, and it's hoped that improved metallurgy or cooling technology might help with the weight and heat issues, bumping the fuel efficiency up. Anyway, getting back to our scramjet, it's very like the ramjet. The difference is mostly about the geometry of that intake. We've actually got some designs for dual mode that would convert the ramjet into a scramjet as it speeds up, and they're good for speeds beyond Mach 6. Needless to say, dual mode is very tempting since you don't need another heavy and inconvenient engine. These are also very appealing for spaceflight because they get much better specific impulse than a rocket, still much lower than a turbofan, but generally about double what a rocket would. The real limitation on them is mostly the fuel and metallurgy. We have other ways of heating things besides burning chemical fuels, but we do still have to worry about melting everything if we get too hot, and we sometimes contemplate doing all this inside a magnetic field with stuff heated to plasma temperatures that avoided actually touching the housing and melting it. We'll come back to that though. Of course, all this makes one wonder why we don't do this then launch the rocket from the scramjet. And you can do that, but keep in mind the scramjet's specific impulse isn't all that much higher than a rocket's, and that's a lot of extra mass and a lot of air resistance issues to deal with. It would also defeat the notion of a spaceplane, something that took off from the ground, went to space, came down, refueled, and was ready to do it again, without discarding any major bits or breaking into separate chunks like a multi-stage rocket does, even the reusable kind. With this approach, you already still have to deal with 3, arguably 5 chunks: your regular turbofan, the turbofan and afterburner, the ramjet, the scramjet, then the rocket. Needless to say, it would be awesome if our material science and metallurgy allowed us to have a turbofan that could fold itself up to be a ramjet, convert into a scramjet, then switch into a pure rocket, possibly with an aerospike, similar in concept to aircraft wings that alter shape to adjust for speed, but much more complex. I should note that such speeds and vehicles might be good enough all by themselves, since they might be able to hook up to a skyhook or rotavator at those speeds, and just be lifted to dock at a space station. Moreover, the basic concept might work just fine if we are using alternative fuels like metallic hydrogen, or an atomic source, or even beaming energy in. More on that later, but if you got planes that can go hypersonic on their own, that makes for very fast travel around the planet, and something that could be linked up to a skyhook, or even coast up to an orbital ring or stratostation. We've had a number of spaceplane designs down the years, and not just on the drawing board. 5 have successfully flown to date, the first being the X-15, and one of those is the Space Shuttle, and these are all considered a type of rocket glider, same as the X-1, first used to break the sound barrier, and the X-15 still holds the speed record of Mach 6.7 for a manned, powered aircraft set 52 years ago. As for the fastest unmanned, air-breathing aircraft, the X-43 has flown up to Mach 9.6 using a scramjet, after being delivered to test altitude by a conventional aircraft and rocket. None of them have flown all the way up to space on their own. Designs have improved, of course, and this is where we get to the Sabre and Skylon. Sabre, or Synergetic Air-Breathing Rocket Engine, is a hybrid air breather and rocket engine currently under development. The approach here is to suck air in as your oxidizer at lower speeds, an air breather, and switch over to a stored oxidizer at about Mach 5 to become a normal rocket. We'll bypass the concept of pre-cooling for today, which allows turbojets to function better at higher speeds, instead of using a ramjet. Skylon is the proposed spaceship for this engine, and it runs on hydrogen and oxygen, sourcing some of that oxygen from the air, then, as we mentioned, switching to onboard stores at Mach 5. Folks always wonder why we can't keep sucking oxygen in, at least until we're up in space, and of course you can, but that causes serious problems as you speed up, and is exactly why you need to switch to a scramjet with supersonic compression when the ramjet can no longer hack it. Skylon estimates they'd sell each spaceplane for about $1 billion, and they get payloads up to orbit for a little under $2,000 a kilogram, with each vehicle able to take off, land, and be turned around in a day or so to complete a couple hundred flights a year. This would have been awesome a decade back, and the remaining technical challenges are pretty manageable. But unfortunately for it, though not for space travel in general, SpaceX has so lowered launch costs that this isn't super attractive at the moment, especially with wrinkles still remaining, let alone a prototype. The Sabre still hasn't been built, which probably can be mostly laid at the feet of funding delays, rather than technical limitations. One other downside for development though, while this series is about getting off Earth and what we can do in orbit, Earth's atmosphere is a fairly specific thing, and rockets work fine on Mars or the Moon, but obviously air-breathing jets aren't really ideal for an airless planet, moon, asteroid, or the vacuum of space. This is what makes a big, mutating hybrid rather appealing. It would be pretty awesome to have a spacecraft with engines optimized to whatever environment it was in, but which didn't have to carry around tons of different engines and exterior shapes, as they just quickly reassemble to the right kind as needed. That seems pretty sci-fi, but it's not something I casually rule out either, especially as we've already got example designs of ramjets converting to scramjets. The other approach is just sheer brute force, if you've got a better fuel source. We'll skip the option of beaming energy to our spacecraft, as we'll be discussing that next time in the series, and that leaves us only one current option, nuclear fission, which we looked at in the nuclear option episode. Though we may also have metallic hydrogen, which we also looked at earlier in the series. If your fuel just offers way more specific impulse, as metallic hydrogen is suspected to do, then it solves a lot of the problems, and suddenly spaceplanes become easy, and actually rather cheap if you've got an abundant energy source for drawing hydrogen out of water and compressing it to its metallic state. Atomic power is obviously far more energy dense than even metallic hydrogen, but a problem with atomics is that whole melting issue. Fundamentally, it's the speed or temperature of the propellant flying out the back that controls specific impulse, and regardless of your energy supply, you can't spit those propellant particles out at super high speed without them being super hot and melting your engine. This is what makes ions such a nice propellant. You're moving them around with magnetic fields rather than metal. When it comes to onboard power sources, we've got many things better than chemistry for energy on the table. Fission of course, but fusion, antimatter, and even micro black holes could potentially be powering spaceplanes down the road, which totally solves the energy issue. But except for fusion, these are generally things you don't want flying around in the sky, or more accurately, crashing into the ground. Nobody wants a hypersonic plane crashing into their house, let alone one full of uranium or plutonium, and those look like minor incidents compared to what a tank full of antimatter or a micro black hole are going to do at the crash site. None of these really sound like something you want your neighbor keeping in their garage either. I mean, a propane tank for the grill is one thing, a bunch of uranium rods or pebbles is another. Even metallic hydrogen is kinda something you don't want people keeping several tons of nearby. Beamed energy is nice in that regard, though again we'll save that for next time. And ideally fusion is nice too, some hypothetical compact aneutronic Mr. Fusion that just makes power as fuel is added and can't really explode. If we have that, then yes, we've got something that will let you keep your spaceplane in your garage and wouldn't have any problem getting you right from there to Mars, especially if it incorporated some fairly quiet vertical takeoff system. And we have been getting good at making helicopters quieter, usually at a big cost in fuel efficiency and power, but again, with fusion and with spacecraft power requirements in general, that would be a minor concern, and would let you do the garage with a top that opens up so you can fly off to work, or the moon. Obviously, while spaceplanes might be in our future, I wouldn't be expecting to see spaceplane dealerships opening up in every town anytime soon. I'd say in our lifetimes, but I'd rather expect we'd have life extension technology before that, which always makes that expression a bit dubious for discussing the far future. So maybe one day we will get to have our own private spaceplane in the garage we can just take out for a quick Sunday drive to space and back. As we talked about the future of spaceplanes today, we talked a lot about the history of aviation along the way, and it's an amazing topic both from the science and engineering angle and from the human one. That pioneering perspective of flight, from early propeller planes to rocketry, is truly inspiring. If you'd like to find out more about that, try out the documentary Pioneers in Aviation on CuriosityStream, one of many great documentaries they have available for viewing on that topic and others. Founded by John Hendricks, the founder of the Discovery Channel, CuriosityStream is the world's first streaming service addressing our lifelong quest to learn, explore, and understand. CuriosityStream is a subscription streaming service that offers over 2,000 documentaries and non-fiction titles from some of the world's best filmmakers, including exclusive originals. You can get unlimited access starting at just $2.99 a month, and for our audience, the first 30 days are completely free if you sign up at curiositystream.com/IsaacArthur during the sign-up process. So we were looking at ways to get off Earth today and out into the solar system, and next week we'll be going to the edge of the solar system to look at colonizing Pluto, and we'll contemplate some colonization methods for other large icy bodies in the Kuiper Belt, along with effective double planets, like Pluto essentially is with its largest moon. The week after that, we'll continue our recent look at black hole technologies and the civilizations around them by looking at how they might defend themselves with black holes in Weaponizing Black Holes. For alerts when those and other episodes come out, make sure to subscribe to the channel, and if you'd like to support the channel, visit our website to donate or look at some of the SFIA merchandise you can get. Until next time, thanks for watching and have a great week.